guys.
Language. And if the property is possessed by this machine, this UTM, then this machine will surely start and give a yes for the input X, as we are taking an possessed by the language, right? So here we have reduced the properties possession problem with the simple problem of accepting a string by the machine M, right? If the machine is accepted by this UTM, then the property is possessed, otherwise the property is not possessed by the language. So last, thus there must be a machine M of L. Now, if the property is possessed, means if this W is accepted by this machine M, then the property is possessed. So we are taking a contradiction here. The property is possessed by this machine, this language, and if the UTM, Universal Turing Machine, is accepting this and property is possessed by this machine, then this is giving a yes, and after this yes, we are again starting a new machine. We are starting a new machine, that is M of L. So now we are running the machine M of L corresponding to this language M of L, and we are accepting one string. We are accepting one string that belongs to M of L. This. So if we have any such machine that doesn't possess this particular property, so the property is not trivial, the property is undecidable and non-trivial, because all the machines are not possessing this property, right? So the proof starts with first step as, let P is a non-trivial property, right? We have already covered this, and as P is a non-trivial property, so it is not possessed by recursively enumerable language L. So we are taking an assumption that this property is not possessed by recursively enumerable language L, and for this language L we are having M dash as a corresponding machine. So this is our M dash, the corresponding machine for this language. The machine that accepts the strings of this language is M dash, and the property is not possessed by M dash, right? Now, second, we are taking the problem can be reduced. So we are taking that problem can be reduced to a smaller problem by taking one universal Turing machine, and we are saying that this universal machine is possessing this property if and only if this machine can accept this input string W. So we are reducing the problem, means the problem of non-trivial property, we are reducing it to simple. This Turing machine and the set and one input string W. So if this universal Turing machine, this UTM with language L of U, so this universal Turing machine is having language L of U. So if this UTM machine will accept W for this M, so universal Turing machine can perform the task of any machine, and we need just to provide the description of the machine and the corresponding input, and the universal Turing machine will give the output, right? So if this universal Turing machine can accept this W for this machine M, then we can say that the property P is possessed by the machine, right? So here, thus we take UTM-U that takes the pair this, the description of a machine and the input string as input, and output yes if and only if the P, the non-trivial property, is possessed by L. If this property is possessed by L, then we can say that, then only then we can say that the property is possessed by the language L. Otherwise, if the W is not accepted by the machine, the property is not possessed by the language, right? So here we have reduced the properties possession problem with the simple problem of accepting a a string by the machine M, right? If the machine is accepted by this UTM, then the property is possessed, otherwise the property is not possessed by the language. So last, thus there must be a machine M of L. Now, if the property is possessed, means if this W is accepted by this machine M, then the property is possessed. So we are taking a contradiction here. The property is possessed by this machine, this language, and if the UTM, Universal Turing Machine, is accepting this and property is possessed by this machine, then this is giving a yes, and after this yes, we are again starting a new machine. We are starting a new machine, that is M of L. So now we are running the machine M of L corresponding to this language M of L, and we are accepting one string. We are accepting one string that belongs to this language. And if the property is possessed by this machine, this UTM, then this machine will surely start, and
thus we take a universal Turing machine U that takes a pair M, W as input and outputs yes if and only if P is possessed by L. Thus there must be M of L is that accepts L and X be a string as X belongs to L. Let P be a non-trivial property that is not possessed by RE language L and M is the machine for it. The problem can be reduced to one consisting of pair M, W such that L possesses P if and only if W belongs to L of M. Thus we take a universal Turing machine U that takes a pair M, W as input and outputs yes if and only if P is possessed by L. Thus there must be M of L is that accepts L and X be a string as X belongs to L. Let P be a non-trivial property that is not possessed by recursive enumerable language L, and M is the machine for it. The problem can be reduced to one pair consisting of M, W, such that M is the description of the machine and W is the input string that is passed as input to the universal Turing machine, such that L possesses P if and only if W belongs to. Thus we take a universal Turing machine that takes a pair M, W as input and outputs yes if and only if P is possessed by L. So that means we take a universal Turing machine that accepts the input, and after accepting the input, L belongs to P, P belongs to L of M. W belongs to L of M. ये जो W है वो करता है L of M को, लैंग्वेज ऑफ मशीन.
give a yes for the input X, as we are taking X belongs to the language L. So X belongs to the language L. That means this.
Let's listen to the other Rice's theorem video by IIT Guwahati.
Turing machine M, whose language satisfies the property. So we saw this existence, and we said that this Turing machine, we called it as M. So what we will assume here is that the Turing machine M prime that we are going to design has a copy of M hard-coded into its description. Of course, it has MW also, but it also has this Turing machine N hard-coded. So let me write it. So M prime has a description of with, of course, M and W. So once again, so how should you picture this? I mean, picture this as, so you want to write a program M prime, or you want to write and design an algorithm M prime. So this algorithm, what it does is that, so inside the description of the algorithm or inside the description of the program, there is already a description of N, M and W that is given in the description. Okay. It's not part of the input, it is part of the description of this program. Now what it does is that, now given any input x to M prime, now we have to decide how will the Turing machine M prime behave on x. So let us, yes, I want to emphasize this fact because this is very important, that all these three things, N, M and W, they are not part of the input. Okay. In other words, they don't change with different inputs. X is what is the input. X is what will change every time you run the program, or it might change. But these three things, they remain constant for every time you run the machine M prime. So first M prime will simulate M on W if M rejects W, then it rejects. Okay, it doesn't do anything. If M
accepts,
accepts
दो चीजें होंगी, तो फिर then simulate n on x.
N
अब ये n on x वाला part जो है,
so if the machine M accepts
Accepts
W, so
W.
here there are two things that can happen. In fact, three things. If M rejects W, then we reject. If M runs forever on W, then of course it runs forever. It never goes to the second stage. But if M accepts W, then what we do is that we take the description of the machine M and we simulate the input to M prime on the machine M. Now, if M accepts, then accept, and if M rejects, then of course reject. So our machine M prime, it is rejecting here once. So if M rejects, it will reject, and if M rejects, then also it rejects. The only time it accepts a string if M accepts W, okay, and N accepts X. So let me write it here explicitly. If N accepts X, then we accept. So now, so that's all. So this is the description of the machine. And now once we have this description, we just output the description of M prime. So now let us see why this reduction is correct. So suppose if M accepts,
अब ये part
we
है,
have is that M comma W
हाँ,
is a yes instance of ATM. So it means that MW is accepted by
universal Turing machine.
a machine that accepts ATM. So if M accepts W, then what we have here is that we
Simulate,
simulate N on X. Then if N accepts X,
then accept.
then we go ahead and accept X.
Okay.
So then the language of N accepted by the machine N. Nothing. All those strings that are accepted by the machine N is nothing but the language of N.
Okay.
Whenever N accepts X, M prime will accept the same X,
Okay.
which implies that. So the language of M prime is the language of N, and we know that. So again, from our assumption, we know that the language of N satisfies the property. It satisfies the property P. So therefore, P of L of m is equal to 1. On the other hand, if m does not accept W, then we don't even go to the next step. Okay, so we don't even go to the third step here. Okay, so we directly reject. So in that case, the language of m prime is equal to 5. Okay, and our assumption was that p of phi is 0, which implies that p of L of m prime is 0. So here actually what I should say is that, so since the language of m prime and the language of n are the same, so therefore p of L of instead of n, I can write this as m prime also is equal to 1. Okay. So what we have here is that if m accepts W, then p of L of m prime is 1, or the language of m prime satisfies p, and if m does not accept W, then the language of m prime does not satisfy p. So therefore ATM reduces to welcome to the 36th. Then we don't even go to the next step. Okay, so we don't even go to the third step here. Okay, so we directly reject. So in that case, the language of m prime is equal to 5. Okay, and our assumption was that p of phi is 0, which implies that p of L of m prime is 0. So here actually what I should say is that, so since the language of m prime and the language of n are the same, so therefore p of L of instead of n, I can write this as m prime also is equal to 1. Okay. So what we have here is that if m accepts W, then p of L of m prime is 1, or the language of m prime satisfies p, and if m does not accept W, then the language of m prime does not satisfy p. So therefore ATM reduces to comma W, and then we give a construction of ATM is undecided. This is that associated with,
Then it has the property. We say that it satisfies the property.
say that means you get L some property is had is of M such that and of languages of Turing machines, if there exists Turing machines M1 and M2 such that
P is said to be a non-trivial property of languages if there exist Turing machines M1 and M2.
P of L of M1 Turing that property, and there is some Turing machine
Which does not
whose
satisfy.
language does not satisfy that property. For example, if I say that if I look at all of these properties, okay, so there are Turing machines whose language is empty, there are Turing machines whose language is not
Not
empty.
empty.
There are Turing machines whose language has 1000 strings, we can construct. There are Turing machines whose language has more than 1000 or less than 1000. Similarly for the first property also. So all these three properties are non-trivial properties of languages of Turing machines. So theorem as follows. Let P be a non-trivial. So
P जो है वो नॉन ट्रिवियल कब है, ठीक है? If there exists P is said to be a non-trivial property of languages of Turing machines if there exist Turing machines M1 and M2 such that PL of M1 is equal to 1 and PL of M2 is equal to 0. तो ये कहता है नॉन ट्रिवियल प्रॉपर्टी को कुछ मशीन्स एक्सेप्ट करती हैं और कुछ नहीं कर सकती. फॉर एग्जांपल मान लो L हैज द स्ट्रिंग 0110. अब कुछ ट्यूरिंग मशीन्स हैं जिनमें 0110 होगा और कुछ हैं जिनमें नहीं होगा, और इन्हीं प्रॉपर्टी को L हैज 0110 को बोलते हैं नॉन ट्रिवियल.
follows. Non-trivial property of languages of Turing machines. Then the language consisting of those Turing machines, I'll call it L subscript P, encodings of machines M such that L of M satisfies P, or I can write it as P of L of M is equal to 1 is undecidable. So if we have a non-trivial property of languages of Turing machines, then the language of encodings of Turing machines whose language satisfies the property is undecidable, which also means that the language of encodings of machines whose language does not satisfy the property is also undecidable, because decidable property
Let P be a non-trivial property of languages of Turing machine. Then the language LP is equal to M, PL of M is equal to 1 is undecidable. Let P be a non-trivial property of languages of Turing machine. Then the language LP, a language of the non-trivial property M, satisfies. तो ये राइसेस थ्योरम की स्टेटमेंट है, ये तो मैंने देखी नहीं है.
So what it means is that, so we had actually already proven for this. Okay, so remember that the language ETM that we had shown consisted of encodings of all those machines whose language was empty. Okay, so that is basically one way to show that. So this, so if we prove Rice's theorem, it gives us an alternate proof of the fact that ETM is undecidable. How do we prove this property? How do we prove the theorem? So we prove the theorem in two parts, in two cases. So case 1. So consider the language phi. Okay, that is the empty language. So case 1 is, so assume that, so we have this property P. Assume that
ml.
Phi is 0, then what we can say is that since P is a non-trivial property of languages of Turing machines, there exists a Turing machine such that the language of, so there exists a Turing machine, let's call it M, such that the language of M satisfies the property, or in other words, P of L of M equals 1. In that, so we have this property P. Assume that P of phi is 0. So if we assume that P of phi is 0, then what we can say is that since P is a non-trivial property of P is a not of machines, such that satisfies the property, or in other words, P of L of M equals 1. So here we have a language which does not satisfy the property. So that means that there must be some other Turing machine whose language satisfies. And of course, we can construct a Turing machine whose language is empty set. Okay? So we just have a Turing machine which rejects all inputs. So we of course have a Turing machine for phi. So now, so using this Turing machine, we will prove that. So using this, we will show that ATM reduces to LP. So recall that ATM is undecidable, so this will prove that LP is undecidable. So what is the reduction? The reduction, let's call it F. So what will F do? So F is a function, okay, which will take an instance of ATM and it will produce an instance of LP. So what F does is that it takes, it's an instance of ATM M comma W, and it will produce an instance, let's say
M dash. सो गाइस ऐसा पॉसिबल है कि अगर आप पढ़ाई करने बैठ जाएं तो आपको जो फन की फीलिंग आती है ना, एंटरटेनमेंट की, मज़े की, वो आपको पढ़ाई में भी आ सकती है. तो इसमें कोई मुश्किल काम नहीं है पढ़ाई करने में. बट द स्टार्ट, अगर आप एक बुरे वक्त से गुजर रहे हैं तो आपको पढ़ाई करने की कोशिश ज़रूर करनी चाहिए यार. मर दो यार, इतना तो सह लोगे. दुनिया ताने मारेगी, तुम पढ़ोगे तो ताने कम हो जाएंगे खुद ब खुद. Yeah, I am studying.